Next, we are going to consider another example. So in this example, we want to evaluate the line integral f dot ds, where our vector field f equals to e to the sin x sin y minus y, comma e to the x cosine y minus x minus 2, and your curve c of t is given by this vector equation. Finally, your t goes from 0 to 1. Now, first let's check whether we could apply the fundamental theorem for line integrals for this particular problem. The first thing we need to do is we want to check whether this vector field is conservative or not. Okay, so since this is a vector field in R2, we have to use the cross partial test to check whether this is conservative or not. Okay, so let's use the cross partial test first. Cross partial test. So in that test, we want to calculate partial q over partial x and partial p over partial y. Now, if these two quantities are equal, then yes, our vector field is conservative. Okay, so partial q over partial x equals to, derivative of e to the x is e to the x, and we have to treat cosine y as a constant. So we have cosine y minus derivative of x is 1. Next, we are going to take the derivative of this first component, which I denoted using p of x comma y with respect to the y variable. So we have to treat x variable as a constant. So we have e to the x, which is a constant. Then we have sine y. Derivative of sine y is cosine y minus 1. As you can see, from this we have partial q over partial x equals to partial p over partial y. This means the given vector field is conservative. Great. So now we could apply the fundamental theorem for line integrals. But in order to apply the fundamental theorem for line integrals, we want the corresponding scalar potential function. So basically we need this f, this little f. Okay, now we know how to calculate this little f. Okay, so let's do that. So this is your f. This is your f, which equals to gradient of little f, and gradient of f equals to partial f over partial x comma partial f over partial y. Again, this vector field is a two-dimensional vector field. So here we have only two components, the first two components of the gradient operator. Now from this, we can say that partial f over partial x equals to e to the x sine y minus y, and partial f over partial y equals to e to the x cosine y minus x minus 2. Now let's find what our little f is. So I'm going to consider equation 1. Okay. Now let's integrate both sides with respect to x variable, with respect to the x variable. If you do that, you will get f of x comma y equals to integral of e to the x sine y minus y, so dx. Since this is a partial integral, we have to treat y variable as a constant. So integral of the first term should be integral of e to the x, which is e to the x, times the constant term sine of y minus y times integral of 1 is x. But now we have to add this, the constant of integration, which in this case it should be a function of y. So let's say this is a function of y. Okay, so now what we do is we take the derivative of this equation with respect to the y variable. So now we take partial f of partial y, which equals to e to the x cosine y minus x plus dg over dy. Now we can compare equation 2 and 3. Let's compare equations 2 and 3. If you do that, you should get this equals to e to the x cosine y minus x plus dg over dy. Now clearly we can cancel these two terms, and then we even can cancel this one. We have the derivative of g with respect to the y variable equals to -2. So to get g, we have to integrate both sides with respect to the y variable. It's -2. If you integrate -2, you will get -2y plus some constant. Great. Now let's update our function f. Okay, and we have an expression for g of y. So we have e to the x sine y minus y x plus, sorry, it should be minus 2y plus c of x comma y. So we have found the general scalar potential function for the vector field. So now, next what we need is the coordinate of the initial point and the terminal point. So to get that, we go back to this parametric equation, and note that t goes from 0 to 1. So to figure out the coordinate of the initial point and the terminal point, we substitute the two terminal t values. So if t equals 0, you will get the initial point. Okay, if t equals 0, this is 0, comma, you will get minus pi over 2 times cosine of pi over 2, because this is 0. Cosine of pi over 2 is 0, so this should be 0. That's the initial point. Now to get the terminal point, let's substitute t equals 1. Okay, so you get c of 1, which is 1 to the power 3, which is 1 times sine of pi over 2, so sine of pi over 2, comma, minus pi over 2 times cosine of pi over 2 plus pi over 2. Sine pi over 2 is 1. Now this is pi. Cosine of pi is negative 1. Negative 1 times negative pi over 2 is positive pi over 2. So here we have the coordinate of the initial point and the coordinate of the terminal point. So next we want to evaluate our function little f at these 2 points. So now we have line integral of f dot dr, so ds, the curve c equals to f at 1 comma pi over 2 minus f at 0 comma 0. Now do not worry about this constant c, because when you subtract these two functions you can cancel this c value. Of course we do not know the exact c value, that is fine. Okay, let's calculate f of 1 comma pi over 2. X coordinate is 1, so you have e to the 1 times sine of pi over 2 minus y coordinate is pi over 2 and x coordinate is 1 minus 2 times pi over 2 plus c. This is the function value at the terminal point. Now let's calculate the function value at the initial point. So x value is 0, y value is 0. If you do that, you will get sine 0, which is 0, and this term is also 0, and the third term becomes 0 as well, and you will get only that constant of integration c. Now as you can see, we can cancel this c value with that. Basically we have e to the 1 times sine pi over 2 is 1, so we have e to the 1 minus 3 pi over 2 minus pi over 2 times, minus pi over 2 minus pi is minus 3 pi over 2. So this is the value of the line integral f dot ds. Okay, if you do not use the fundamental theorem for line integrals, then you have to evaluate. So then this is your x coordinate and this is your y coordinate, and think about substituting this value over here and substituting this value into the y will give you a very complicated expression which may or may not be able to solve using a regular integral. But here fortunately our vector field f was a conservative one. Because of that we were able to find the corresponding scalar potential function little f, and using this scalar potential function and the fundamental theorem for line integrals, we calculated the exact value of this line integral.